Good morning everyone. Welcome to this another video lecture on recurrence relation. Today we're going to learn how to solve a linear non-homogeneous recurrence relation with constant coefficient, which can be defined where a of n can be written as c1 times of a n minus 1 plus c2 times of a n minus 2 and all the way up to ck times of a n minus k and plus f of n, and whenever f of n is not equal to 0, we will say this is a case of non-homogeneous recurrence relation. Since all those coefficients c1, c2, c3 all the way up to c of k, they are constant, so this is the problem with the constant coefficient, and all the terms a of n terms of your sequence, they are connected with this linear relationship. So this is an example of a linear recurrence relation. So on combining all those facts together, we will say a recurrence relation which can be written of the following form is an example of a linear non-homogeneous recurrence relation with constant coefficients. Whenever you have a case of a non-homogeneous recurrence relation where this term f of n is not equal to 0, you can also get an associated homogeneous recurrence relation with respect to that. If we just put f of n terms equal to 0, then the above recurrence relation will reduce to the following form where the contribution of the fn term is 0. Now to solve this non-homogeneous recurrence relation, we'll combine the solution of the homogeneous recurrence relation and with a particular solution which is responsible with respect to this non-homogeneous term. So the idea is whenever you have a non-homogeneous recurrence relation, you're going to look at the associated homogeneous recurrence relation of that and find the solution of that homogeneous recurrence relation, and then you look at the particular solution with respect to the non-homogeneous part, and then by combining the solution with respect to the homogeneous as well as the particular solution, you will have the complete solution of your non-homogeneous recurrence relation. Let's define what you mean by the particular solution in case of your non-homogeneous recurrence relation. So a particular solution of a recurrence relation is the one that satisfies the recurrence relation but not necessarily the initial condition. So for an example, we have a case of a non-homogeneous recurrence relation here where a of n is connected with a of n minus 1 plus of 1, and the non-homogeneous term f of n is going to be equal to 1 here. The initial condition a of 0 is equal to 5, and this relationship is true for every value of n greater than equal to 1. So a particular solution for this case could be if you just assume that a of n is going to be equal to n, because this a of n is equal to n will satisfy your recurrence relation, but it does not satisfy the initial condition a of 0 is equal to 5. So you can check it here. The a of 0 is going to be 0, which is not going to be equal to 5. So it does not satisfy the initial condition, but it satisfies your recurrence relation. So your recurrence relation in this case is a of n is going to be a of n minus 1 plus of 1. So this side is going to be n, this side is going to be n minus 1 plus of 1. Once you choose this choice of your particular solution, that a of n is going to be equal to n, then if you simplify, you will see n is going to be equal to n. Now to obtain the solution of a non-homogeneous recurrence relation, we're going to use this theorem. And based on the statement of this theorem, we are saying suppose we have this non-homogeneous recurrence relation where this part f of n is not going to be equal to 0. And let's suppose it has a particular solution which is a n of p, and the associated homogeneous recurrence relation with respect to that will have a homogeneous solution part which is a n of h. So once you have the homogeneous solution part and you have a particular solution part, you can combine both of them, and then every solution of this non-homogeneous recurrence relation can be written as a of n is going to be equal to a n h plus a n p, where this is your homogeneous part of the solution and this is your particular solution. Okay, so we're going to use this idea in obtaining the solution of a non-homogeneous recurrence relation. So our overall idea to find the complete solution of a non-homogeneous recurrence relation is based on the concept that we find a particular solution, and then we already know a systematic way how to find the homogeneous part of the solution that satisfies the initial condition, and by combining both the solution we can have the complete solution of our non-homogeneous recurrence relation. Let's look at how you're going to apply this theorem on solving some of the problem with the help of this example. And this time we have a non-homogeneous recurrence relation which is given in the form of a of n is related with 3 times of a n minus 1 plus 2 of n, and a of 1 is going to be equal to 3. So this is true for every n greater than or equal to 2. My initial condition is a of 1 is equal to 3 here. The non-homogeneous part of this recurrence relation f of n is 2 of n, which is not equal to 0. Okay. Now the first step to obtain the solution of this non-homogeneous recurrence relation, we're going to look at the solution of the associated homogeneous recurrence relation. And the associated homogeneous recurrence relation you can obtain with respect to this non-homogeneous recurrence relation by putting f of n is equal to 0. And if you put f of n is equal to 0 in your given recurrence relation, then your recurrence relation will convert to a of n is going to be equal to 3 times of a n minus 1. And then we can apply our characteristic equation based method to find the solution of this homogeneous recurrence relation. Okay, so our characteristic equation, just by putting a of n is equal to r to the power n, where r is not equal to 0 and is a constant. Okay, you can convert this relation a of n is equal to 3 of a n minus 1. This side will be r to the power n, this side will be 3 r to the power n minus 1. Okay, so you obtain this equation. And once you divide the both side by r to the power n minus 1, so this side becomes r and this side becomes 3, and you can write the characteristic equation of this recurrence relation is going to be equal to r minus 3 equal to 0. So when you look at the roots of this characteristic equation, you only have one root, which is r is equal to 3. And based on our concept of the previous lecture, we can say the homogeneous solution part of this equation, we can say is going to be an of h, and h is for the homogeneous solution, is going to be equal to some constant time the root, which is 3 here, to the power of n. So once we obtain the homogeneous part of the solution, the next step is to find the particular solution, a n of p, and we're going to look at this non-homogeneous part in our recurrence relation, and the non-homogeneous part was f of n is going to be equal to 2 of n, which is basically a linear function in a term of n. So we can assume a trial function of the same order to obtain the particular solution. So in this case, the trial function which we're going to use is, we are saying our particular solution a n of p is going to be a general polynomial of degree 1. And we can represent a general polynomial of a degree 1, which is a linear function, by the term c of n plus of d, where c and d are any constant. So they are the real constant. Okay, so depends on my given term f of n, and if f of n is a linear function, my particular solution is going to be a general linear function. Okay, and I can represent a general linear function based on by choosing two constants c and d, such that a n of p becomes c times of n plus of d. Since my particular solution will satisfy my non-homogeneous recurrence relation, but it's not necessarily true with respect to the initial condition, so my non-homogeneous recurrence relation is going to convert into that form once I put a of n is going to be equal to a n of p replaced by the particular solution. So the left hand side a n of p is going to be your c of n plus d. The right hand side is going to be 3 times of c of n minus 1 plus of d, and this is the representation of your a n minus 1 of t is going to be equal to c times of n minus 1 plus of t. Okay, and plus 2 of n terms remain as it is. And once you simplify and collect the coefficient of your nth term and the coefficient of your constant term, and this side becomes your 2 of c plus 2 times of n plus 2 of d minus 3 of c equal to 0. And if you compare the coefficient of 1 and coefficient of n from both sides, then you can say this side you can write as 0, which can be written as 0 times of n plus 0 times of 1. So the coefficient here is 2c plus 2, and the coefficient here is 0 with respect to your n term. This gives you the first equation that 2 of c plus 2 is going to be equal to 0. The coefficient of the first term, one term, is going to be equal to 0 here. The coefficient of one term is going to be 2d minus 3 of c here. So if you compare the coefficient, is going to be your second equation, 2 of d minus 3 of c equal to 0. So once you have these two equations, you can use them to obtain the value of c and d. And from your first equation, 2 of c plus 2 equal to 0, this gives you the value that c is going to be equal to minus of 1. Once you have the value of c equal to minus 1, you can obtain the value of d. From this equation, d is going to be equal to minus 3 by 2. Okay, and by putting the value of c and d into your particular solution, your particular solution a n of p will become minus of n minus 3 by 2. Once I have a particular solution in hand, I can use the statement of my theorem. The complete solution of this non-homogeneous recurrence relation will be the combination of your homogeneous part of the solution and your particular solution. And a of n can be written as a n h plus a n p, while my a n h was alpha times 3 to the power n. My a n p part, which comes out to be minus of n minus 3 by 2. So my general solution a of n with respect to this non-homogeneous recurrence relation will becomes minus of n minus 3 by 2 plus alpha times 3 to the power n. And we are saying this is general solution because we still have a constant present in this solution alpha, and alpha could have any value. And since alpha could have any value, it's going to say is a general solution. So this general solution is going to satisfy your non-homogeneous recurrence relation, but to say is the solution of your given problem, we need to find the value of this alpha, and which can be obtained based on the concept that this general solution should satisfy your initial condition. So your initial condition in this case, given problem was a of 1 is going to be equal to 3. So you put n is equal to 1 in your general solution. So this side becomes your a of 1 and this side becomes your minus of 1 minus 3 by 2 plus alpha times 3 to the power 1. And if you simplify, then the value of alpha comes out as 11 by 6. Okay, and if you put this constant alpha is equal to 11 by 6 in your general solution, then the complete solution of your given problem, non-homogeneous recurrence relation with the initial condition, will becomes a of n is going to be equal to minus n minus 3 by 2 plus this constant 11 by 6 times 3 to the power n. And now this solution is going to be a unique solution of your problem, and there is no constant involved, so we are not going to say it's a general solution. Now it's become your unique solution of your given problem. So just to recall what we did, so with respect to any given non-homogeneous recurrence relation, first you look at the associated homogeneous recurrence relation form. You find the solution of that homogeneous part. Okay, then you're going to look at your particular solution, and once you obtain your particular solution, you're going to combine this particular solution with your homogeneous part of the solution, and that's going to give you the general solution. If the initial condition is given in your problem, then whatever constant is involved in your general solution, you can obtain the value with respect to them, and the idea is just to use the initial conditions and your general solution satisfy the initial condition. Based on that, you obtain those constant values, and after that, after putting the value of your constant in your general solution, then your general solution becomes your unique solution of your given problem. Let's look at another problem, and this time we're supposed to find all the solutions of this non-homogeneous recurrence relation, where a of n is going to be equal to 5 times of a n minus 1 minus 6 times of a n minus 2 and plus 7 to the power n, and there is no initial condition given in this problem. So we are supposed to find the general solution instead of the unique solution. Okay, and we are looking for all solutions which could be possible in this case. Okay, so this is a recurrence relation of degree 2, and this is a non-homogeneous recurrence relation where my non-homogeneous part f of n is going to be equal to 7 to the power n. It's not equal to 0. Okay, so my idea to solve this non-homogeneous recurrence relation remains same. So the first step is I'm going to look at the associated homogeneous recurrence relation. With respect to that, I'm going to obtain the solution of that homogeneous part, and then I'm going to look at the particular solution, and then on combining both the solution, I can have the complete solution of this problem. So in my step 1, I'm trying to find the homogeneous part of the solution. So the homogeneous part you obtain, just put a f of n equal to 0 in your equation, then your recurrence relation will become a of n is going to be equal to 5 times of a n minus 1 minus 6 times of a n minus 2. Then with respect to this homogeneous recurrence relation, you will have a characteristic equation of the form r square minus 5 of r plus 6 is equal to 0, which can be factorized as r minus 3 times r minus 2 equal to 0, and the characteristic roots of this characteristic equations, they are r1 is going to be equal to 3 and the second root r of 2 is going to be equal to 2. Since you have two distinct roots, then from our previous lecture we can write the homogeneous part will have the solution of the form that alpha times 3 to the power n plus beta times 2 to the power n, where alpha and beta are two constants. Then we move to our second step, and in our second step we're supposed to find the particular solution of this problem. We're going to look at the non-homogeneous part in this given recurrence relation, and the non-homogeneous part here is f of n is going to be equal to 7 to the power n. So we will assume that our trial function in case of our particular solution will be of the same kind, but in a general sense. So 7 to the power n is going to be some kind of a exponential function. We can say in general you can represent is going to be c times 7 to the power n, where c could be any constant. Okay, so you assume this is your particular solution, and then you use the idea of your particular solution is going to satisfy your non-homogeneous recurrence relation, which is a of n is going to be equal to 5 of a n minus 1 minus 6 of a n minus 2 plus 7 to the power n. So you replace a of n by the particular solution a n p. So this side becomes your a n p, this side becomes your 5 of a n minus 1 p minus 6 times of a n minus 2 p plus 7 of n. Put a of n of p as c times of 7 to the power n. Then your a of n minus 1 p becomes c times 7 to the power n minus 1, and a of n minus 2 p becomes your c times of 7 n minus 2. So once you replace your a n p, a n minus 1 p, a n minus 2 p in the above equation, so this will reduce to the following form, that this side becomes your c times of 7 to the power n, this is your 5 times of c times of 7 to the power n minus 1 minus 6 times of c times of 7 to the power n minus 2 plus 7 to the power n. Then you divide the whole both side, the whole equation by the factor 7 to the power n minus 2, and this will reduce to the following form, that this side will be your 49 of c equal to 35 of c minus 6 of c plus 49, and if you simplify to get the value of c, then c comes out to be 49 divided by 20. Okay, so your particular solution here in this case becomes equal to 49 divided by 20 times 7 to the power n. Okay, and then we can write the general solution of this problem, which can be obtained by combining a of n can be obtained by combining the homogeneous part of the solution a n h plus the particular solution part of the solution, which is your a n of p, and a n of h from above is going to be alpha times 3 to the power n plus beta times 2 to the power n, and this particular solution is 49 divided by 20 times 7 to the power n. So on combining both of them, we'll get the solution of our given non-homogeneous recurrence relation will be of the following form, where alpha and beta are constant. Okay, so we don't have an initial condition, we cannot obtain the value of alpha and beta. So in this case, this will represent the general solution of my recurrence relation, and they represent the all possible solutions of this recurrence relation. So through these two examples, we have learned that if you are interested in the solution of your non-homogeneous recurrence relation with some initial conditions, then you can obtain the solution of those problems just by finding the solution of your homogeneous recurrence relation part in the first step. Then in the second step, you're supposed to find the solution of your particular solution. Then in the third step, you're supposed to compute those constants which involved in your general solution, which you can obtain based on your given initial condition. So the first step we know how to do in a systematic way based on our previous lecture. The third step, we can obtain the value of those constants based on our initial conditions. So the only difficult part is the second step. How do we find this particular solution? How do we come up with some kind of a trial function which you can use as a particular solution for your given problem? Okay, and those problems can be solved based on this given theorem. So the theorem says that consider a non-homogeneous recurrence relation. A of n is going to be equal to c1 times of an minus 1 plus c2 times of an minus 2 all the way up to ck times of an minus k plus your f of n, where f of n is the non-homogeneous part, which have a certain kind of form, and the form which we are interested here in this theorem is going to be a product of polynomials of degree t in terms of your variable n, and multiply with some kind of exponent where s to the power n. So if you have those kind of a non-homogeneous part in your recurrence relation, which can be written as the product of a polynomial of degree t in terms of your variable n and some s to the power n. So for those kind of a non-homogeneous term, we can have a systematic way to get the trial solution which could be a possible candidate for your particular solution. So we'll have the following two cases here. So the first case is depends on this term s to the power n. So if this s is not a root of your associated characteristic equation, then the particular solution a and p can be written as a general polynomial of degree t in terms of a variable n, okay, and multiplication of s to the power n, where these constant p0, p1, pt minus 1, pt, they are the general constant. Okay, so we are saying if s is not the root of your associated characteristic equations, then you can write the particular solution of the following form. So you replace this polynomial of degree t in terms of your variable n to a general polynomial of degree t in terms of your variable n, and then s to the power n is going to remain as it is. Okay, so remember in the example of f of n is equal to n, so which was only a linear function, we took a particular solution a and p of the general form such that c of n plus of t. So here you have only one example of the linear function. Here now you can have many linear function, depends on the value of c and t. Okay, similarly you can think of another example. If f of n is going to be equal to n square, which is a quadratic polynomial, so in that case you can choose your particular solution a n of p is going to be a general polynomial of degree 2, which you can represent as b of n square plus c of n plus of t, where b, c and d, they are constants. While the second case of this theorem says that if s is a root of multiplicity m of your associated characteristic equation, then you can have a particular solution a and p of the form a polynomial of degree t in terms of the variable n with the product of your s to the power n terms, and then you have to do one more product which is n to the power m there. So whenever the s, if it's present in your non-homogeneous form here, if that s becomes your roots of your characteristic equation and it has a multiplicity of m, then you're going to multiply this n to the power m terms in your particular solution, and everything else is going to remain as it is. Let's look at some example and how you're going to apply this theorem to find the particular solution for this given problem, where a of n is given equal to 6 of an minus 1 minus 9 of an minus 2 plus some f of n non-homogeneous part. So let's suppose in the first case my non-homogeneous part is 3 to the power n. Then what I will do, first I'm going to look at the associated linear homogeneous recurrence relation form present in my non-homogeneous recurrence relation, which in this case is a of n equal to 6 times of an minus 1 minus 9 times of an minus 2, which you obtain just by putting f of n equal to 0 in your non-homogeneous recurrence relation. And if you look at the characteristic equation with respect to this homogeneous recurrence relation part, so you will have a equation of the form r square minus 6 of r plus of 9, which can be written as a factor of r minus 3 times r minus 3, which is r minus 3 whole square equal to 0. So the roots of this characteristic equation is r is equal to 3, which is repeating 2 times, so the multiplicity m is going to be equal to 2 here. Now if you look at your non-homogeneous part, which is given in your problem, which is f of n is going to be equal to 3 to the power n. So this 3 is going to be your characteristic roots with a multiplicity 2 with respect to your associated characteristic equation. And based on your result of this theorem, you can say my particular solution a n of p is going to be equal to n to the power m, and n to the power m in this case is n square. Then since f of n you are writing as 1 times 3 to the power n, so you will have a constant term. So you can generate a constant term by putting a general constant p of 0, and this s to the power n term, which is 3 to the power n here, is going to remain as it is 3 to the power n. So you're going to write your particular solution is going to be of the form n to the power 2, because your m is 2 here. Then you will have a general constant p0 times 3 to the power n. So that's going to be the particular solution of your problem. Similarly, you can extend the result of your theorem in the case when your f of n is n times 3 to the power n, and this s is going to be equal to 3 here. You will have a linear function here, which is n. So your particular solution based on your theorem is going to be based on n to the power 2, because this roots 3 is going to have a multiplicity of 2, and then you're going to product with a general polynomial of degree 1, which you can write as p0 plus p1 times of n, where p0 and p1 are constant, and this factor is going to remain 3 to the power n there. So the particular solution can be written as the product of 3 terms, n square times p0 plus p1 of n, and multiply by 3 to the power n. Your next problem is, let's suppose we have a f of n, which is given as n cube times 2 to the power n. So now the s terms here is 2. If you just compare with your statement where f of n is written as some polynomial of degree t in terms of n multiplied by s to the power n form. So s in this case, if you compare these two, will be equal to 2, and p of t of n is a polynomial of degree t, is basically your n cube here. Okay, so based on your statement of the theorem, you're going to apply the first case of the theorem. So based on your case 1, since the characteristic roots of this equation is 3 and the value of s in this case is 2, so my particular solution in this case is going to be a general polynomial of degree 3 multiplied by 2 to the power n. Okay, and general polynomial of degree 3 I can obtain by just putting this constant p0 plus p1 of n plus p2 of n square plus p3 of n cube, and p0, p1, p2 and p3, they are the constant here, and this factor is going to remain same, 2 to the power n here. So I can apply this theorem in finding the trial's particular solution with respect to my non-homogeneous recurrence relation. Now we are going to apply this concept of recursive function as well as how to solve a non-homogeneous recurrence relation in solving a puzzle problem, which is your Tower of Hanoi problem, given by a French mathematician in late 19th century by Edouard Lucas. So the problem is you have three packs. Okay, so pack 1, pack 2 and pack 3, and the initial position is the pack 1, they contain n number of disks. Okay, and the disk is put in a certain specific order. The largest disk is going to be at the bottom, the smaller disk is going to be on the top. So the goal here is to move all the disks from your pack 1 to pack 2. And the rules which going to follow in moving all those disks from a pack 1 to pack 2 is based on that the larger disk cannot rest on the top of the smaller disk. Okay, and second, you can only move the topmost disk at a time. So by following these two rules, the goal here is to move all the disks from a pack 1 to pack 2. And the question is, in how many steps does it takes to move all those n disks from a pack 1 to a pack 2? So to solve this problem, you can have an idea that suppose my number of disks in the case is only 1. So if I have one disk and I have these three packs, so if I have only one disk, so the number of moves which I need to make to move this disk from a pack 1 to pack 2, I can take this disk and I can move it here. So the number of steps is going to be only 1. Okay, so the number of step is going to be equal to 1. Okay, so if I have only one disk on a pack 1, I can make one move and I can move this disk from a pack 1 to a pack 2. Okay, let's look at another scenario, and this time you have for example, you have two disks and you have two disks on a pack 1. Okay, so you have a larger disk and then you have a smaller disk, and now see how many number of moves you need to make. So in the first step, what you can do, since you have a pack 1 here, you have a pack 2 here, and then you have a pack 3 here. Okay, so in the first step, you take this smaller disk and you move it to this pack 3. Okay, this is the one step. Then in the second step, you take this larger disk and you move it to the pack 2. And then in the third step, you take this smaller disk from a pack 3 and then you move it on the top of this larger disk. So this is your step 3. So the number of step or number of moves which you have to make in solving this problem when it will have two disks is going to be equal to 3. If you again look at this case of two number of disks on your pack 1, so this problem you solved by just moving the n-1 disk to a pack 3 and then moving this largest disk from a pack 1 to pack 2 and then moving this n-1 disk from a pack 3 to pack 2. So this is a 3-step process. Okay, so using this as an algorithm, we can have the solution of this problem as a recursive solution. So assume that T of n is the number of steps which are required to move n disk from a pack 1 to another pack. So in the base case, when you have n is equal to 1, which you have only one disk on a pack 1, then the number of steps which is required based on our example which we discussed before, then you just required one step. You can take that disk and you can move from pack 1 to pack 2 and then you have the solution of this problem. Okay, so if you look at the base case of your this recursive solution, then in that case, if T of n represent your number of steps which you require to move n disk from a pack 1 to another pack, then T of 1 is going to be equal to 1. Then you can apply the concept of induction, and based on the concept of induction, you assume that to moving the n-1 disk from one peg to the another peg, you require t of n-1 steps. And then the question you are trying to solve that how many number of steps you will require which to move n disk from one peg to the another peg. Okay, so the idea is based on our second example which we took for n is equal to 2 number of disk. So the idea here is first you take the top n-1 disk. Okay, so you take the top n-1 disk and you move them from your peg 1 to peg 3. And since you are moving this n-1 disk from a peg 1 to peg 3, it's going to take t of n-1 steps. Okay. In the second step, now you can move this larger disk from a peg 1 to this peg 2. So move the bottommost largest disk from a peg 1 to peg 2, and it's going to take only one step. Okay, so when you move this one disk from here to here, it's going to take only one step. Okay. And finally, by using this as a recursive approach, you can move those n-1 disk from a peg 3 onto your peg 2, and you're going to follow all those rules. So in moving here, you're going to take a t of n-1 steps. Okay. So this puzzle can be solved by using this recurrence relation. The t of n, which represent the number of steps is going to take to move n disk from a peg 1 to peg 2, can be solved by t of n-1, which is the number of moves or steps you're going to take by moving the top n-1 disk from a peg 1 to peg 3, plus t of n-1, which is going to be the number of moves you're going to use to shift those n-1 disk from a peg 3 to peg 2, and only one steps which you required when you move your largest disk from your peg 1 to peg 2. Okay, so remember we had n disk and we have these 3 pegs. So the topmost n-1 disk, first we moved here to this peg 3, if this is your peg 1, peg 2, peg 3. So this is going to take your t of n-1 step. Then you take this largest one and you put it here on the peg 2, from peg 1 to peg 2. This you can do in only one step. And then you move those n-1 disk again from a peg 3 to peg 2 to solve this problem, which is again going to take t of n-1 steps. Okay, so you are saying your t of n is going to be equal to t of n-1 when you move them from a peg 1 to peg 3, and plus 1 when you move a larger disk from a peg 1 to peg 2, and then t of n-1 when you make the move of the n-1 disk from a peg 3 to peg 2. Okay, so in total you can say the total number of steps which is required to solve this puzzle is going to be 2 times of t of n-1 and plus of 1. Okay, so you can represent this in the form of the following non-homogeneous recurrence relation, that your initial condition is going to be t of 1 is going to be equal to 1 when you have only one disk on your peg 1, you just required only one steps. And the total number of steps which are required in the case when n is greater than equal to 2 is given by this recurrence relation, that t of n is going to be equal to 2 times of t n-1 plus of 1, which you can verify that when you have 2 disks, then the solution of this problem is 2 times t of 1 plus of 1, which is going to be equal to 3. And if you recall in our example which we did before, so we required 3 steps when we are trying to solve this problem for n is equal to 2 number of disks. So this is an example of your non-homogeneous recurrence relation of degree 1, where you have the given initial condition, and you can try to solve this problem by the two approach which we developed in these lectures. The first approach, if you remember, was your iterative method. So if you trying to solve this problem by using your iterative method, you can write the t of n terms can be written as 2 times of t of n minus 1 plus of 1. And then you can reuse this relation in writing your t of n minus 1, which can be written as 2 times of t n minus 2 plus of 1. And you replace this t of n minus 1 by this term 2 times of t n minus 2 plus of 1 by using this relation, which if you simplify can be written as 2 square times t of n minus 2 and plus of 2 plus of 1. Okay, and again you reuse your recurrence relation that t of n minus 2 can be written as 2 times of t of n minus 3 plus of 1. So you replace t of n minus 2 by this quantity, and then you will have is going to be 2 square times 2 of t n minus 3 plus 1, and plus 2 plus 1 is going to remain same as we have before, which if we simplify can be written as 2 to the power 3 times t of n minus 3 plus 2 square plus 2 plus of 1. And if you keep on doing in this downward direction, you can write the t of n expression as equal to 2 to the power n minus 1 times t of 1 plus 2 to the power n minus 2 plus 2 to the power n minus 3 plus all the way up to 2 and plus 1. Where if you use your initial condition t of 1 is equal to 1 here, then t of n can be written as the sum of the power of 2 to the power I starting from I is equal to 0 all the way up to n minus 1. So this is your t of n. Now if you use a result which you can prove by using your mathematical induction, then the sum of 2 to the power I, and when your index I will go from 0 to k, is going to be equal to 2 to the power k plus 1 minus of 1. And if you apply this result here for the value of k equal to n minus 1, then 2 to the power k plus 1 minus 1 becomes 2 to the power n minus of 1. So the solution of this problem is 2 to the power n minus of 1, which is going to satisfy your case that t of 1 is going to be 2 to the power 1 minus 1 is going to be equal to 1. So I required only one move to move a disk 1 to from a peg 1 to peg 3. While if you compute t of 2, then it's going to be 2 to the power 2 minus of 1, which is going to be equal to 3. So which verify the case when you have one disk, you require only one step. When you have two disks, you're going to require 3 steps. So you can write the closed form of the solution with the help of this expression 2 to the power n minus 1 in solving this tower of ni problem by using your first method, which is based on your iterative approach. Let's look at our second method, which is based on this characteristic equation, which we'll learn in today's lecture. So to write your solution of your non-homogeneous recurrence relation, you're going to look at the homogeneous part of the solution, then you're going to look at the particular solution, you're going to combine them to get the general solution, and then if some constant are involved and you have the given initial condition, you can use them to obtain the value of those constant to get the unique solution of your non-homogeneous recurrence relation. So by following that approach, we can write the solution of this tower of ni problem. So you can say my recurrence relation which is given here is t of n is going to be equal to 2 times t of n minus 1 plus of 1, and this is true for n greater than equal to 2, where you have the initial condition t of 1 is equal to 1. Then the associated homogeneous recurrence relation with respect to this non-homogeneous part is going to be, once you put this f of n equal to 0 in this equation. So if you put f of n equal to 0 in this non-homogeneous part, you will have the homogeneous recurrence relation part, which is your t of n is going to be equal to 2 times of t of n minus 1. When you look at your characteristic equation, so you can obtain the characteristic equation with respect to this linear recurrence relation by putting t of n is going to be equal to r to the power n, and t of n minus 1 is going to be equal to r to the power n minus 1. Once you put here in your given in your recurrence relation, this side becomes r to the power n, this side becomes 2 times r to the power n minus 1. If you divide both sides by a factor of r to the power n minus 1, then your characteristic equation becomes r minus 2 is going to be equal to 0. So the roots of your characteristic equation, which is your characteristic roots, in this case is going to be r is equal to 2. So the homogeneous part of the solution with respect to this associated linear recurrence relation will be Tn of h is going to be equal to c times of 2 to the power n, where c is a constant. Now to get the particular solution, you're going to consider your non-homogeneous term, and non-homogeneous term is f of n is going to be equal to 1, and 1 is a constant. So based on your above theorem, you can get the particular solution Tn of p, which is going to be a general constant which you choose as a beta here, and beta is a constant. So the general solution can be written as the solution of your homogeneous part and the particular solution. So the general solution T of n is going to be equal to c times 2 to the power n plus of beta. Now you can try to obtain the value of this beta, and the beta is the particular solution, and by the definition the particular solution is going to be satisfying your recurrence relation. So you choose this particular solution T and P is equal to beta, and it's going to satisfy your recurrence relation, which is your non-homogeneous recurrence relation here. T of n is going to be equal to 2 times of Tn minus 1 plus of 1. So you replace T of n by Tn of p. So this side becomes Tnp, this side becomes 2 times of Tn minus 1 p plus of 1. And since it's a constant, so this side is going to be equal to beta, this side is going to be equal to 2 times of beta plus of 1. And if you simplify, you'll get the value of beta as minus of 1. So the particular solution in this case is going to be equal to your minus of 1. And since the general solution was the combination of your homogeneous part and the particular part of the solution, so the homogeneous part was c times 2 to the power n, the particular solution is minus of 1, so this will be the general solution of this problem, where c is a constant. Now this constant can be obtained once you satisfy your initial condition. So your initial condition here is T of 1 is going to be equal to 1. So if you put n is equal to 1 in your general solution, this side becomes your T of 1, this side becomes your c times 2 to the power 1 minus of 1. And if you simplify, then the value of c will come out to be equal to 1. Okay. Once you put c is equal to 1 in your general solution, then you will have the unique solution of this problem, and the unique solution of this problem comes out to be 2 to the power n minus of 1, which is the same solution which you obtain by using your iterative method approach. So in this lecture, we have learned how to use a systematic method in solving your non-homogeneous linear recurrence relation with a constant coefficient problem. And we also look at one example which can also be solved by using your earlier approach based on your iterative method. And this is going to conclude our lecture on recurrence relation topic. In our next lecture, we're going to look at the approach of divide and conquer, and then we're going to learn about master theorem. And after that, we're going to move to the number theory, which will be your last topic in this course. And we're going to spend 4 lectures on that, and that's going to conclude your the syllabus of discrete math course.